In the last chapter, you were guided through the calculation of a one-sample z-test. In that case, the one-sample z-test was appropriate because you knew the population mean and you knew the population standard deviation. Well, it turns out that in a lot of cases, the population standard mean is known, but the population standard deviation is not known. And so when you don't know the population standard deviation, you must do a one-sample t-test. So this is in the case where you have a sample mean, a sample of kids that you've studied or adults that you've studied, and you want to compare their mean score on some variable, in this case a math performance test, to a population mean performance test value. So here I have the numbers that we're using in this example. Here's the population parameter. The mean of the population is 474, and remember this number refers to the mean math test performance score for the population of kids that are the same age as this sample. And the sample mean is made up of 75 teenagers, all of whom were exposed to the special math curricula throughout their elementary and early high school years. And the question that we're asking is the mean performance of these kids, and we're judging that from the mean math test performance score, which is 478 for this population. So does this differ significantly from the population? Right? So our N is 75, the mean math test performance value for this sample of 75 kids is 478. The standard deviation is 80. The sum of squares has been calculated for you and is 19,440, as given in your book. Every one of you should know how to calculate sum of squares, and I hope you can picture exactly how that was calculated. If you're forgetting how to calculate sum of squares at this point, go back and refresh your memory, because it's very, very important that you have a very concrete understanding of what sum of squares is telling you. Your alpha level, which you selected, is 0.05. It's a standard 0.05 alpha. The t-critical value we determined to be 2.0 for this problem, and the degrees of freedom, n-1, for one sample t-test is 74. So there's 3 simple steps that you do to get your t-value. The first step is to estimate the population standard deviation. Remember, we use a one sample t-test because the population standard deviation is not known, so you have to estimate it. And interestingly, you estimate it from the characteristics of your sample data. And notice that we use a different symbol when we're estimating population standard deviation. Remember, when population standard deviation was known, we used that symbol, right? But we're not going to use that because we don't want to mislead anybody to think that this is a known value. This is an estimated value. So we use a small s. Estimated population standard deviation equals the square root of the sum of squares of the sample divided by the degrees of freedom, n-1, which of course in this case will be 74. So then the second little step, second easy calculation, is to estimate the standard error of the mean. And we estimate that using the estimated population standard deviation. So estimated standard error of the mean equals the estimated population standard deviation divided by the square root of our current sample size, which is 75. And then finally, once we have those two numbers done, we can calculate our t-value for this test. And the t-value is calculated by taking the mean value of our sample, subtracting from that the mean value of the population, and dividing by the standard error of the mean. Very straightforward, right? So let's do this together. You'll see how fast it goes. All right, so let's start with getting our estimate of the population standard deviation. Very easy. We know that the sum of squares for this sample was 19,440 divided by n-1, which is 74. And if you do that calculation, let's do it on a little calculator here. So you see there's no trickery. Divided by 74 equals 262.70. Right? and then we get the square root of that, and we find that rounding to 2 decimal places, we get 16.21. Okay, very cool. So that's easy. Estimated standard population deviation for this particular problem is 16.21. And of course, we're going to use that up here. So here's S, and we're going to do this, say 16.21 divided by the square root of 75, right? And of course, we'll do this together. Square root of 75, if you want to see it on the calculator, should be 8.66, so it's 16.21 divided by 8.66. And when you do that calculation, you find that the value is 1.87. Okay, so 1.87 is our standard error of the mean. Now remember, that's the amount of variability you could say that we would expect by chance alone. Now calculating your t-value is very straightforward. We know that the mean of the sample, big M, right, capital M, was 478. And I always like to check my numbers, so just go back here. Yep, 478. The population mean is 474. Divided by the standard error of the mean, which is 1.87. Simple. Now we have 4 divided by 1.87. And so our t statistic comes out to be 2.14. Easy, right? All right. Now, of course, in the next step, you'll evaluate this result. But before we go on to those next steps, I want to point out something here. What is happening in this step? What are these numbers doing? Think about that for a second. This ratio is comparing the amount of variability between your mean values to the amount of variability that would be expected by chance alone, right? And notice something. If our mean value for our sample was not 478, but instead was 476.13 minus 474, and we divided that by 1.87. Now this is not what our values were, I'm just doing a little demonstration here. What t-value would you get from that? When there is no difference between the amount of variability between the sample, and in this case the population that you're comparing it to, and the amount of variability to be expected by chance alone, your t-value is 1.0. Zero difference, right? Very good.